Okay, guys, do you see my screen and do you?
Yeah.
Yeah. Okay. Super. Perfect, guys. Um, First of all, thank you what I'm allowed to speak here and give a presentation. I would like to apologize if you get some noise from the background. I mean, I'm on vacation now and there could be some noise, so don't care about that. And I would like to ask you, please all maybe to turn off the cams because my internet is maybe not that stable here. So maybe it's maybe easier to not get some problems. So guys, I would like to speak today about high resolution transmission spectroscopy of a super Earth, which is 55 Cancri E. So, and I would like to go immediately to atmospheric characterization. So how do I characterize atmospheres here? Or we all, I mean, we also know very nice explanations here. So this is a transiting planet and the blue dashed lines show the transiting planets. So what we do now during the transit is we observe photons which are scattered and absorbed by the planetary atmosphere. And we can observe during the transit the planetary fingerprints using, for instance, spectrographs. And such atmospheric fingerprints can look like this here. I mean, you have transmission spectra, and then you can see some spikes showing some absorption by atoms and molecules. So I'm doing it quite quick. So as we saw during the planetary transit, the planet moves towards us and away from us, and we are observing it with telescopes from Earth. And what happens is the following, that during the planetary motion, the planetary absorption arises shifted on top of the stellar line, which is shown here in blue, and the planetary absorption, yes, can then be also tracked on different orbital phases on top of this. So what we then do is following, we use the all in transit observations and take one mean out of transit observations. So here are your in transit observations, and you divide by a master out of transit observations. And what you get is what you want to see is absorption signature and transmission spectra arising at different positions, which regard to the orbital phase of a planet and its the velocity of a planetary atmosphere. However, this is an easy method which can show you fingerprints of atomic species, for instance, which have strong opacities in atmospheres, such for sodium or potassium. However, if you have lines which don't have such strong opacities, you maybe need to combine different lines. And Matteo also showed a very nice, and also different authors showed very nice illustrations now for the cross correlation method. So what you do is like you combine different lines. So on top left and on top right, I am showing an observation, for instance, in red, and the left plot has a planetary atmosphere included and the red not. And then you shift your template, which is shown in blue. And if you get something nice, some nice match, then you get a nice peak at the radial velocity of 0. I mean, if you take your transmission spectrum, which is combined. However, the situation may be changed if you increase your noise level, then the match is not that easy to see, then you will again get a peak maybe. However, this all depends on the noise level of your observations and also on the amount of lines you use to do a cross correlation. Okay, so the major question I am asking myself is, the main thing is, why do I care about atmospheres? Is because you can compare exoplanet atmospheres to the solar system planets, and this maybe can give us clues about the evolution of planets and maybe of our own solar system. A very good target for such an investigation is 55 Cancri E, which is a super Earth. I mean, absorption from gaseous exoplanets are easy to resolve, as we see. I mean, as we also saw in the previous talk, because we have large scale heights and large atmospheres. However, one day we would like to go to terrestrial planets and maybe also in the future to Earth-like planet where we can maybe trace some signature of life. However, if we start with terrestrial planets, maybe the Super 55 Cancri is one of the best targets because it has a very bright host star of 6 magnitudes. This target has around 8 Earth masses, 2 Earth radii, and the orbital period of around 0.7 days. So what does this mean? This means this planet is very close in. So this planet gets a lot of harsh radiation and is maybe more comparable to a target in our solar system, which we call Mercury. So Mercury has no atmosphere and is the closest planet in our solar system. However, it has an exosphere consisting of different species which are spotted by solar irradiation. And here we have different detections for this planet, for instance, potassium, calcium, and magnesium, and so on. Now, I mean, we have 55 Cancri is a super Earth. However, it's comparable to Mercury. And now let's have a look maybe for 55 Cancri and what is found out now for atomic species. Only I'm concentrating here for 55 Cancri. So until now, for 55 Cancri, primary atmospheres could be ruled out. So there's no detection of hydrogen and helium until now in high resolution. However, there's evidence of sodium and calcium shown by Ridden Harper. I mean, the authors do not state real detections, although they have a nice significant signal. However, there's a non-detection also by Tabernaro et al. For the sodium feature. It's a bit difficult to compare both observations by Ridden-Harper and Tabernaro because Tabernaro et al. Used quite lower resolution, and also the authors have quite large exposure times where they could maybe smear out the sodium signature. So maybe it's let's say it's not that sure if there's sodium or no sodium, and there's a tentative detection, but there's no detection. However, the calcium signature looked very large, but other major species now, like oxygen, potassium, and magnesium, have not been yet investigated for 55 Cancri E. Now, for the atmosphere of 55 Cancri E, two scenarios are favored. So the first scenario is that there's no atmosphere. Yes, that we have only a rock, and that we get maybe something stubborn out. There's a non-detection of water and maybe evidence of calcium and sodium, so which maybe could favor this scenario. However, there's the second scenario which says there could be a heavyweight atmosphere. Also, there's the shifted hotspot detected on this planet, and to shift the hotspot, you usually need atmospheric circulation processes, and so you would need a heavyweight atmosphere which shifts your hotspot into a direction, and this would hint on a heavyweight atmosphere, and also other authors investigated stuff which hints on that. However, the atmosphere of this planet is still puzzling, yes, and both scenarios are still valid because no of the authors could also exclude the other scenario. So what we are now doing here is the following. We want to add another puzzle piece to that work, investigating the atmosphere of this planet during transit. So we want to investigate the question if maybe this planet could have an exosphere full of spotted species which arise from a rocky surface. What we do now is the following. We think that 55 Cancri E could have an Earth-like crust composition. If we have looked to the Earth-like crust, you see that we have a lot of sodium, silicium, aluminum, and so on. Here we have a composition in percentage. And what we do now is following. We look for all those species in the transmission spectrum of 55 Cancri E and cross-correlate also templates to look for them. So their presence would hint on a rocky surface scenario, whereas if we don't see something, this would give another hint maybe that there is a heavyweight scenario. Yes, because if we have a rocky surface, we would get some sputtering out of some material. Okay, how did we observe the transit of 55 Cancri E? For that, I used a large binocular telescope, and we combined it with a Pepsi instrument. The large binocular telescope is the largest telescope in the Northern Hemisphere. It has 2 × 8.4 meter mirrors, which you combine, and the Pepsi instrument is in high resolution spectrograph stabilized, and we use the observation in the wavelength regions, which I will show also later, and we use the exposure time of 90 seconds. By the way, I would like to mention that Pepsi is the spectrograph with the highest resolution mode which can be used, because you can use it in a 60,000, 120,000, and also 250,000 resolution mode to observe transiting planets. Yeah. So use Pepsi. Okay, guys. Here I am showing example spectra which I got from the wavelength range which we covered. So on the top, we have a wavelength range covered in the blue arm of Pepsi from 4,800 to 5,400 angstrom, in the bottom from 7,400 to 9,000 angstrom. We have only one transit, which is pity. However, we have an amazing data set. We have more than 40 in transit and 40 out of transit spectra with a signal to noise at the continuum per pixel of 500 to 700. It's an amazing data set, and it was a lot of fun to work with it. We have here, as you can see, oxygen telluric lines, major amount of them, and also water telluric lines, which is a bit making all the investigation a bit more difficult. Transmission spectrum I showed you, you can see the different, you can create a transmission spectrum. However, you can combine them by co-adding all of them into one line of sight. and this is the combined transmission spectrum, and you see the residual fluxes, which are very low. Yes, I mean, however, also you can see again that the telluric lines, to get rid of them, but this was also not a problem because the species which we investigate has no major lines at the regions where we mask the telluric lines. So let's now go to the results. I will now show some cross correlation maps, and what I will show is an example here. So on the top, you can see the templates which I use. The template looks like this. We only use the white ranges, a white range here, a white range here, and so on. Yes, the red region is the wavelength region which we do not cover by PEPC in this observation. I mean, we can cover it, but not in this observation. And the green shaded regions are the regions which we masked out, which are the telluric contaminated regions. In the bottom part, I will also show the cross correlation match where we would expect a peak exactly at 0 velocity. Yes. So if we have a signal, look to the cross correlation maps now, which I will show. At 0, we expect something to Z. So I also divided the cross correlation by the standard deviation of a cross correlation function, as Matteo was telling. This is a good first hint. And the 3 sigma is shown at red, 5 sigma at green, and 10 sigma at the yellow dashed lines. And let's now go to see what we see for the different species investigated. And it will be a lot of stuff now showing. I will always show 4 species in a row. So let's first go to the investigation with less abundant atoms. Top left, phosphor, manganese, barium, strontium, and so on. And as you see, guys, at 0 velocity, always take care about 0 in all plots. We don't see something for the minor species. Not here. Also for the other minor ones, we don't see something now. I mean, I'm now going to be a bit more fast. So the less abundant species do not show something. However, for instance, for chromium, we also have lines. I mean, several amount of lines, but we don't have so many lines for all species. Now let's first of all go to different species. So first of all, for oxygen, we don't see something. However, note, we don't have much lines. Yes, I mean, it's also, so maybe if we would have a full wavelength coverage and would have more lines, it would be maybe a better case to investigate. So here we can say something. However, for silicium, for instance, I may be a bit too fast, sorry for that. For silicium, we have a lot of lines, and silicium is a major abundant species in Earth crust. We don't see something. So aluminium and H, we also have nothing. And let's go now to iron, which has a lot of lines.
3
Top
minutes
left
left,
is iron. Yeah.
3 minutes.
And also for iron, 3 minutes left.
Yeah, 3 minutes.
Oh, okay, perfect. I will be done in 3 minutes. We don't see something for the calcium, titanium, and so on. For sodium, we don't have resonance lines. So yeah, okay. For calcium and magnesium, we also do not see something. I will be a bit more fast now. However, I am also showing the transmission spectra. On top, you can see the transmission spectrum here in blue and here in black and bint, and we can probe atmospheric absorption above 1.7 radii at a level of 3 sigma. No hydrogen, no magnesium. Also, we can probe atmosphere until 1.7 radii here. Also, we don't see such things. However, also of course potassium, and here we even probe 1.3 planetary radii. I am now going also to ionized species, because ionized species could be maybe valid because it's a very hot planet, yes, and also for them the minor species do not show something. However, let's go to the more abundant species, and here, guys, we have something which we see, and what's that? I mean, this is a bit confusing here because the only species which we see is a calcium signature there. However, this signature, it goes down and not up. I mean, absorption we go up, yes, and a downgoing future would mean there's some emission. If I look to the transmission spectrum of a calcium line, bint and unbint, we would probe 1.5 planetary radii if we would say this is only a spurious signature. However, this is a bit intriguing now. I mean, those are preliminary results, and I am still working on that. However, such a signal would hint on emission, but the signal is very broad, yes. And I don't think that this has planetary origin. However, the investigation is still ongoing. But if some of you guys have some ideas why this could be the case, please ping me on Slack. However, it's interesting. I mean, let's now go to the conclusion of the talk. So we don't see the major amount of species in Earth's crust showing emission, showing absorption in the transmission spectra of 55 Cancri E. So our investigation also hints on a heavyweight atmosphere, therefore, which could be available on 55 Cancri E. Okay, and that's the conclusion. And thank you guys for your attention.
Thanks very much, Engin.
And you can turn on again the cam if you want, guys. Thank you.
Thanks very much.
Am I on time?
For questions, Sarah.
Hi, Engin. Thanks for your talk.
Hi, Sarah.
My question is, how do you deal with the stellar activity? As far as I know, this is relatively active star, and this is a small planet. So how did you check for that?
I mean, I'm not sure if this is a relatively active star. I mean, for 55 Cancri E. But I mean, I checked the calcium infrared lines from the stars and calculated the equivalent widths over the observational course of time, and I don't see any change in the equivalent widths of the calcium infrared lines. So this is the first hint that there is no stellar activity going on. However, I mean, for the calcium, you are right. The calcium infrared lines are, are known to show activity, are known to be activity indicators. So maybe this is also something which comes from a stellar activity thingy.
Yeah, but that's only that shows the flare. So you didn't have any like photometric observations simultaneous, maybe to help you to better.
We did not observe it simultaneously.
Maybe
However,
also unsimultaneous can give you some, if you have a long, I don't know what we have in the archive, but if you have long-term photometric observations of that, maybe it's worth to have a look.
Yeah.
Hey, Jens.
Hi there, Engin. Very nice, nice effort. The slide you've got up is actually really useful. You say you've had two scenarios that you favor. One is no atmosphere, and one is a heavyweight atmosphere.
Yeah.
Given that this planet has a radius of 2 Earth radii, and it therefore sits quite far, I think quite securely above the 1.6 Earth radii Fulton gap, how would you interpret that in comparison with your results? How likely would you say it is that you're looking at a bare rock that is 2 Earth radii in size? And if you are enriched in that, or if your radius is partly due to retaining hydrogen helium, which is what sort of mini Neptunes do, how heavyweight do you think the atmosphere will be able to get? Is it even fair to call this a super Earth, and shouldn't we be calling this a mini Neptune instead? And if so, what happens to the atmosphere then?
I mean, there are investigations of hydrogen helium. Yes, I mean, if it would be a mini Neptune, maybe it would be there would be a more hint on the hydrogen helium observations. Maybe, I mean, the investigations, and I mean, there are density measurements for this planet which must be a super Earth, and also there are like, I mean, there's investigation which says that this planet might have a 1.4 bar atmospheric pressure, and that I mean, there are investigations of water, and they are saying that they're calculating the weight of water amount in the atmosphere. I mean, I am not that sure if this explains your question.
Well, yeah, I mean, we can continue this on Slack maybe, but I think it's really puzzling and interesting to see that on the one hand, this is a fairly large, presumably more mini Neptune-like planet, if you believe this whole Fulton gap theory. And on the other hand, for years, people have been trying to see things, and they come up blank every time. So I think that is very interesting.
I mean, also it's very interesting to think about. I mean, it's so in such close orbit. I mean, I cannot imagine how an atmosphere shall survive on such a planet. Yeah, but I mean, it has also 8 Earth masses, so the gravity might be so large that it might survive. So
yeah. Well, very nice.
Okay. Thank you to all the speakers of today. We're going to pick this up in about half an hour's time, where we're going to hear